Okay, so people on Zoom missed some part, but you can maybe rewatch it on YouTube later. So I was talking about this transient liquid-assisted growth method of superconducting films, of REBCO superconducting films that was developed in our group. And I will be talking about one of the routes that lead us to the formation of the REBCO phase. And this is the pressure route. And the pressure route consists of heating of the nanocrystalline film of precursors based on barium carbonate, copper oxide, and yttrium oxide in low enough oxygen partial pressure. So we blocked the growth of REBCO during the heating ramp until we reach a desired growth temperature. So we can control at which temperature we actually initiate the growth, but by performing a fast pressure jump in oxygen, going to the region of the phase diagram, TILAC phase diagram, where a liquid, transient liquid is can be formed. And then the REBCO grows from the transient liquid. So of course, this process is ultra fast and is quite novel. So there was a need of advanced characterization in order to understand and control this process. So this was achieved with in-situ synchrotron radiation-based X-ray diffraction first. So we, of course, in order to meet all the requirements of the TILAC process, the pressure route especially, and also the acquisition during this in-situ process by X-ray diffraction, we needed to develop a special new experimental platform that would allow both. And this was done by first buying Anton Parr's hot stage, which controls the heating ramps up to the temperatures up to 1100 degrees C. And it is specially designed for acquisition of X-ray diffraction data because the reaction volume is enclosed by the graphitic dome. This hot stage then is connected to two pressure circuits. One of them, the first one, is the low pressure circuit. This circuit controls the oxygen pressure conditions during the heating ramp to the set temperature, and also is able to monitor the evolution of all the gaseous products of the reaction. Especially here, we are interested in the evolution of the carbon dioxide from the barium carbonate decomposition, which is needed in order to form the transient liquid. Then we have a high pressure circuit, which controls the oxygen partial pressure conditions during the TILAC growth after the pressure jump. And this is achieved with a set of mass flow controllers based on oxygen and nitrogen gas mixtures. So we can switch between these two in a fraction of a second and change the conditions inside the reaction chamber in a fraction of a second. So I would like to just briefly show you how the design and building of this evolution from ICMAB here. First, we started to assembling everything in one of the laboratories in the MATGAS, where we assembled everything on the bench of the laboratory. You can see this is the Anton Parr hot stage. We just connected to the set of tubings, needle valves, some gas lines, and pressure readers. Then we needed to fit this into a specially designed frame that would be fitted later to the experimental rack at ALBA Synchrotron. And after testing all of this instrumentation and everything worked correctly, we were ready to move it then to ALBA and fit it to this experimental rack on wheels that permits easily moving it to the beamline hatch and outside the beamline hatch. Everything luckily fitted inside, so we could start with the validation and calibration of this setup. And first, we did it next to the beamline hatch of the NCD suite beamline, where we had access to the gas bottles that we needed for our process. And we have developed the control, operation, and analysis softwares. We could calibrate and validate the setup. And most importantly, we were able to integrate it into ALBA's framework and devices control system, which is called Sardana. And thanks to all of this process, we were able to perform our first in-situ experiments. In 2022, this was done. But before I go to the experiments of in-situ X-ray diffraction TILAC, I would like to just mention that now our experimental platform seats in the Energy Transition Joint Laboratory that was inaugurated at the end of 2024. So during 2 years, we were next to the beamline, but then we moved finally to the laboratory. And this laboratory, as Teresa already mentioned, was built in the scope of PTI Trans-Energy platform that was coordinated by Professor Rosa Palacin from ICMAB and counted with the participation of Professor Teresa Puig. And of course, this laboratory is dedicated to advancing of the energy materials, specifically that of batteries here and superconductors. So now this TILAC setup doesn't, it works also ex situ. It operates ex situ in order to advance the knowledge already and be able to know what kind of experiments are needed in situ in order to better understand and control the process. So now let me go to this part of this talk, which is in situ X-ray diffraction during the TILAC process. And I would like to say that we have been using variety of samples as with different thickness on different substrates, with different rare earths and liquid compositions. And we were varying growth parameters, temperature and oxygen pressures, and always using the fast acquisition rates down to 0.1 second per frame. So this is how it looks like in the beamline hatch of NCD suite beamline. You can see our Anton Par hot stage is placed on top of the beamline stage, permitting us to use the movement of all of the motors available at the beamline. And our experimental platform is just next to it. We've, of course, some pumps placed on the floor. We are also connected to the gas lines through the metallic tubings, which are placed outside the hatch. And we are using the Ryonix 2D CCD detector with a sample detector distance of 300 millimeters. And of course, as I mentioned already, we use fast acquisition rates down to 100 milliseconds per frame, which is very important for this very fast growth process. So we have carefully selected the beam energy that we will use for our experiments. And finally, we end up with 18 kilo electron volts. That permits us to get access to all the crystalline phases of the process, starting with the precursors, the copper oxide, yttrium oxide, and barium carbonate, then going through the intermediate phases, barium, copper, oxygen, and then finally getting information on the epitaxial and non-epitaxial phases of the YBCO or other REPCO. So here I just wanted to show you a very short video of how our data looks like. And I'm sorry for this contrast. It's not very well seen maybe, but I will try to explain it. So here, this part, we can see two-dimensional diffractogramma appeared at the speed of 0.1 second per frame, which is time correlated with the information from our setup on temperature in red, pressure in blue, which is really, I cannot even see it here, and the resistance in green. I have luckily marked the jump moment of the pressure jump, where you can see the growth is immediately initiated, and we can see the reflection of the 0.05 YBCO appearing immediately after the jump. There are also a little bit of the secondary phases of the random-oriented YBCO. And here I have already plotted, but I will have to start it over because there was a zoom, the evolution around the jump of all the phases. And there are the precursor phases and then YBCO. This is the epitaxial and non-epitaxial ones. So it was very important for us to strictly correlate the information on every XRD point with the information on temperature, pressure, resistance, and mass spectrometry signal. And this allowed us to build these kinetic non-equilibrium phase diagrams with confidence. And we can calculate the growth rate of this process by two methods. First is from the intensity increase of the 0.05 reflection of the YBCO, the epitaxial one, or from the inverse of the resistance curve. The critical step for the successful C-axis growth of REPCO phase is the barium carbonate decomposition. And so that's why we follow the evolution of the carbon dioxide throughout all the heating ramp and the dwell time in order to know when all the barium carbonate already decomposed and will be ready to be incorporated in the transient liquid. So the data volume and complexity is high, so we had to develop a lot of analysis and data processing programs. And this one is done first by Jordi, but then was updated by Ona and Emma. And this permits us now to quantify all of the present crystalline phases and plot the evolution with time and also with temperature and pressure. And we can see here one example where during the heating, we see the barium carbonate crystalline phases from XRD, which is decomposing, and also copper oxide is reducing to the copper 2O, and then forming, both of them are forming barium copper 2O2 phase during the heating ramp, and this is also correlated with the mass spectrometer signal of the CO2 gas. Here in the black line is actually the resistance of the film during all of the process. And this is thanks to the samples provided by Ona, where she can prepare the electrical contacts and we can measure inside of our setup. This gives us very nice information also about the growth rate and all the process. So when we go to the pressure jump, we can see that we can grow highly epitaxial YBCO films, which is also here followed with the conductance in this case. This is a conductance curve. And if we zoom in into the very first seconds after the jump, we can see that actually there is a little bit of the randomly oriented grains. However, they reorient into fully epitaxial film after just 10 seconds here. So we studied different rare earths. Here you can see the plots from YBCO, gadolinium, and erbium BCO. And they have wide processing windows of Z-axis orientation, which are controlled actually by the rare earth. They are different for gadolinium, yttrium, and erbium. And this is a part of the PhD work of Carla. And of course, we could calculate the growth rate dependence on the growth parameters. And it is plotted here for YBCO and erbium BCO. And this is easy to see here that the growth rate increases with the increasing oxygen pressure and temperature. And it ranges from 20 to more than 5,000 nanometers per second. So, of course, for one rare earth composition, our experiments are very well suited and they are quite fast. However, if you would like to study the substitution, for example, of one rare earth with another, we would have to use many samples in order to get some conclusions. So our approach was to use the fast screening approach with mixed REPCO compositions we called compositional gradients. And for that, we use inkjet printing machine, where we input the bitmap image of compositional gradients here between yttrium and gadolinium, which can print on a 10 by 10 substrate the compositional gradient of precursor solutions. And this was confirmed by EDX elemental mapping, where each pixel can tell us what composition actually, what ratio of yttrium to gadolinium we obtained in each pixel. Then we go to the NCD suite beamline and we do some ex-situ experiments. We acquire rocking curves around for the 005 epitaxial reflection of the YBCO. And we could see that actually we could get full gradient of compositional from 100% gadolinium to 100% yttrium, a very nice epitaxy at only one condition. Then we, of course, also checked the angle corresponding to the maximum intensity of the REPCO 005 reflection epitaxial peak. And we can see the differences between gadolinium and yttrium, which is consistent with the Bragg's law because the yttrium is much smaller and gadolinium expands the lattice parameter. So here we have a higher 2 theta degrees because we have a smaller d spacing. However, if you would like to perform in-situ experiments on these gradient samples in order to save a lot of time and have 20 different compositions in one experiment, this is still not possible, but this is only due to the motors of the stage that doesn't permit us to move fast enough in order to during the pressure jump with this ultra-fast growth process, be able to see actually how the growth occurs. So till now, I have shown you that in-situ X-ray diffraction gives us very nice information about the all crystalline phases evolution during the TLAC process. And this is perfect. However, we were always conscious that we lack some information. And this is information about any amorphous phases that could be present during the process. And of course, the information about the liquid itself. So we decided to go to another beamline, which is dedicated to X-ray absorption spectroscopy. It's called CLAES at ALBA, which is suitable to all kinds of materials. It can probe even liquids. And we can obtain different complementary information from XANES and from XAFs. So from one part of the spectrum, we can obtain oxidation state, the information on unoccupied electronic state, spin state, local structure, and direct information about the bond angles. While from XAFs, we can obtain bond distances, coordination numbers, static and dynamic disorder. So we have checked if our in-situ experimental platform could fit into the CLAES beamline, and we were very successful. We could fit all of this instrumentation inside and place our hot stage on the beamline stage with the help of a specially designed holder by the engineer of the beamline. And so we could use exactly the same setup. We could use the same sample composition and architecture like in the in-situ XRDs. We use the same growth parameters, temperature and oxygen pressure. And also, finally, I will show you we were able to use the same acquisition rates of 0.1 second per point. So first, I would like to introduce that we were focusing on the copper KH, which is found around 9,000 electron volts, because it has very nice spectral differences between copper 2+, copper 1+, and copper 0. So we can follow very well the transformation of the phases during TLAC. So what we expected was to see during the heating ramp, we would expect the transformation of the copper oxide with the valence state 2 to the barium copper 202 solid phase of valence state +1. Then, during the pressure jump, what we expected to see is a transformation of this solid phase into the transient liquid. And here, actually, at the beginning, we were not sure what we were expecting to see, because we didn't know if the transient liquid would incorporate oxygen or not. And therefore, if when we grow the Rebko phase, the transient liquid would have all the necessary oxygen to form directly the Rebko phase, or there would have to be some oxygen diffusion outside from the liquid, outside of the liquid to form the Rebko. So usually, if you are familiar with X-ray absorption spectroscopy, you should know that one of the spectra takes around a few minutes to acquire. So, of course, this short-lived transient liquid phase, we wouldn't be able to see actually. So we had to go and look for a solution, and it was in the use of the binary samples. And what I mean by binary sample is that instead of using all of these 3 nanocrystalline precursors, we only use 2 of them, the copper oxide and barium carbonate, which are the ones that actually form the transient liquid. And we didn't introduce any rare earth oxide. This permits us to go to the transient liquid, which is quite stable through time. So I will show you now, we've done a lot of experiments, but I will show you just the representative ones, okay? 2 of them. One, which is here at this point of the phase diagram, where we expect copper to be in the +1 oxidation state. So we have performed this in-situ experiment of TLAC, and as we expected, the copper oxide transformed using the heating ramp to the solid barium copper 202 phase of copper +1, which is seen from the blue spectrum to the yellow one. And then right after the pressure jump, we got this red spectrum, which indicates the transient liquid. And of course, you may have some doubt if it's really the liquid phase or not. So we perform some XAFs also in order to see if this is really liquid, and we compare it to the transient liquid spectrum is the pink one, if you can see it well. Then we have the barium copper 202 solid phase, which is the green one, and the copper 2O reference spectra, which is the purple one. And as you can see, the first shell, which indicates the copper O, copper oxygen bonds, the intensity of this first shell is decreased a lot. And then there is total disappearance of the second shell and the following shells. And this is clearly indicative of a disordered liquid phase. So then I will show you also an other extreme of the phase diagram where we were expecting to obtain copper +2. And the same happened. First, we see the transformation of the copper oxide into solid barium copper 202, a transformation of copper 2+ to 1+. But then after the pressure jump, as again, the red curve is another type of liquid. And we can see that it's really similar to the copper +2 fingerprint. However, if we wanted to grow real REPCO, and this is very fast process, this 2 minutes of acquisition wouldn't help. So we had to adapt another approach, which was the fast scan approach, where we selected only this one single energy, which is indicative of this peak, which is characteristic to copper +1 oxidation state, and gives big spectral differences between copper +1 and copper 2+. And then just scanning across during the pressure jump with 0.1 second per point of acquisition rate. And you can see for this the same exact process parameters, we get very nicely, we can see the intensity of the copper +1 and then very sharp drop to the copper +2 valence state. And this allowed us to make many experiments also with the ternary samples, actual growths of REPCO films. I will show you only a few of the most highlighted results here. This is the phase diagram of TILAC for the binary samples, where we've plotted the calculated copper valence state. And it is clearly seen that if we sit at the same temperature and increase the oxygen partial pressure for the liquid formation, and that will be also the growth condition, we have increasing copper valence state. And this will happen for any other temperatures. However, if we sit at the same oxygen pressure and we increase or decrease temperature, the valence states seem to be similar. However, if we use ternary samples where we get the growth of REPCO, we can see that especially for these lower valence states, we obtained a big increase in the valence states due to the REPCO formation. So now, since we used exactly the same experimental platform, we used the same type of samples, we used the same growth parameters, and we used also the same acquisition times, we were confident enough to try to correlate the in-situ XRD data with the in-situ XAS data. And actually, this worked quite well. Here in the zoom out, you may maybe not see very clearly if this works or not, but if we zoom in to the first seconds after the pressure jump, we can actually see that there is an increase of the copper valence state. However, then it decreases a bit. And this can be really correlated with a secondary phase, copper O, which has exactly the same shape as we can see the changes of the copper oxidation state. And when the copper oxide disappears, then the valence state stabilizes to the final REPCO film. And if we have a closer look at all of the process and the correlation of the valence states with the crystalline phases from the XRD, we can see that first, this is the copper valence states, starting with copper +2 from the copper O. Then we can see the reduction of the copper valence state to the copper 1, which is also followed by the blue line, which is the XRD signal quantification of the copper 2O phase. Then this is the first stage. In the second stage, we can see the transformation of the copper 2O in the barium copper 2O2 phase. And then there is some stabilization time before the jump. And finally, we can see the increase in the copper valence states because of the formation of the YBCO. So now, from these correlative in-situ XRD and in-situ XAS experiments, we were quite confident that to get a good understanding and control of the TLAC process. However, we still missed some information, and we are missing the information about the nucleation process. And of course, we believe that this is a critical step that determines the performance of the final REPCO films. So if you want to study the REPCO nucleation on STO by TLAC, you will find that the YBC nuclei grow from the liquid phase at the interface with STO. They will grow laterally and compete for space and material until they will meet each other and coalesce. Then we will have a first continuous layer that will grow through thickness until reaching the surface of the final film. And we know that being in a high or low supersaturation, meaning high or low nucleation density, will influence the growth and determine the microstructure, defect structure, strain structure, and electronic properties of the final film. And this will, of course, translate to the superconducting performance of the final REPCO. So we find a way to study the nucleation process, also at the synchrotron, ALBA Synchrotron, with a new technique, grazing incident small angle X-ray scattering, shortly GSACs. And this time, we are at the same beamline, the NCD suite beamline, but this time we are using different detector. This is the SAX detector, which needs very long flight tubes in order to get the signal to the detector. And we use 6-meter long flight tube in this case. So we were able to use exactly the same setup as we always use for the in-situ growth, but we had to change a bit the architecture of the sample. We needed to lower considerably the concentration and the thickness of the samples in order to get information on the nucleation process. But we use the same known growth parameters for the epitaxial growth and the same acquisition times. So probably not many of you are familiar with the GSACs technique, so I will just briefly introduce the concept of this. So in GSACs, the beam hits the sample at very low angles that are close to the total reflection of the critical angle of the total reflection of the beam. And this permits us to get very high sensitivity to the surface where the nucleation occurs and the growth also occurs. And we get as a signal the two-dimensional scattering pattern in reciprocal space. So instead of giving the real image in the image in the real space, how GSACs works is that it measures the physical parameters of these islands, nanoscale objects, and plots them as a function of the scattering vector Q in Y direction and Z direction. And this we can translate to the real dimension in the real space, such as height, diameter, and interparticle distances through these equations, doing some horizontal and vertical cuts of the GSACs image. And what we really wanted to obtain from this is to obtain the morphological details about the formation of the first REPCO nuclei during the TLAC process, in order to get the size, shape, and spatial distribution of the nuclei, which also is supported by AFM imaging and modeling. So, of course, we couldn't go directly to the GSACs without knowing anything about the nucleation of REPCO on STO by TLAC. So we did some preliminary studies with atomic force microscopy. So we grow these samples at the same growth conditions, and we allowed the nuclei to grow different times, called the dwell time here. So here you have the image after 20 seconds of growth, 150 seconds of growth, 5 minutes, and 10 minutes. And what we extracted from these images are the information on particle density in purple, interparticle distances in green, then the mean particle diameter in blue, and mean particle height in orange. And as you can observe, at the beginning, we can see that the particle density increases until some point. Here it's 5 minutes, and then decreases after 10 minutes. And this is inversely correlated with the interparticle distances as expected. And of course, the mean particle diameter and particle height are steadily increasing throughout the time. So this is just, these plots were done just on Friday. So I'm just showing them to you that we are really able now to plot the vertical and horizontal cuts of the GSACS images, time correlated with the temperature and pressure of our experimental setup of our experiment, TILAC experiment. And this is an ongoing analysis, so I cannot give you more details about it. But I can already see here that it looks very promising because there are some changes just after the pressure jump. So we will be going with the ongoing analysis. What we have done for now is to do some atomic force microscopy imaging of the in-situ sample and compare it to the one of ex-situ. And as you can see, they look quite similar. The only thing that maybe the density is a bit different between the two, and the interparticle distance, which the two characteristics are, of course, linked together. However, the diameters around 35 and 31 for both growth, and the heights around here 5 and 3.5 are quite similar if you think about statistic. And also, if we take into account the standard deviation error, they actually fall into the same ranges. So this is quite promising study. Now I will just jump to another subject of our work on TILAC, which is the industrialization of the process. And in the group, we are working on different aspects of that. Here in the PhD of Vittorio and Dr. Roxana Vlad and Dr. Silvia Rassi, they work with the metallic substrate that are relevant for coated conductor technology. And they could prove that they are compatible, the TILAC process is compatible with the industrially relevant deposition techniques, such as slow die coating, for example, where we can obtain long tapes and very high C-axis growth. And this attracted the interest of the industry, of course, and being the Faraday factory from Japan, the most interested in the TILAC process, and actually starting very close collaboration and even investing into TILAC process, R&D. So we have even performed some in-situ XRD experiments with the TILAC process on with the industrial beam time of the Faraday factory with our setup and our process, where we got very nice results till now. So this is very getting closer to the industrial setting. There is another aspect of the TILAC industrialization, which is the scaling up and the scalability studies. Here were led by Dr. Cornelia Pop that were able to scale up the precursor salts preparation and also the precursor solution preparation, which led to the patent of invention. She's also leading the preparation of the nanoparticles that can be introduced into the TILAC film to work as a pinning centers, vortex pinning centers. Another aspect is making the tapes longer and wider. As I told you in the figure of Merning of reducing the cost to performance ratio, these are also important aspects to have in mind. And this is led by Dr. Roxana Vlad and is a part of the PhD of Vittorio. So our final goal is industrialization of TILAC for coated conductor technology. And the most interesting applications for us are the superconducting cables for lossless energy transport and compact fusion reactors for plasma confinement by high magnetic fields. And here I would like to just summarize, and I hope you get some understanding of the TILAC and of the work of in-situ synchrotron radiation techniques in order to understand this process. So I would like to just highlight that due to the novelty and the ultra-fast growth nature of TILAC method, the in-situ synchrotron experiments are essential to understand the mechanisms of TILAC growth, and that the setup installed at ALBA is a key element for that purpose. The in-situ XRDs provide essential information on the mechanism of the crystalline transformations throughout the process. However, the correlative in-situ XAS complements this information with the liquid and valence state information. And additionally, now the information on the reponucleation during TILAC by in-situ GSAC has a big potential to further advance the knowledge on the mechanism of the REPCO formation during TILAC. So with that, I would like to acknowledge of the people that work on this project, especially the SUMAN group. All of them have been to the beam times and work on the samples preparation and data analysis. And also would like to acknowledge our local contacts, Eduardo Solano from the NCD and Laura Simonelli from CLAES, because it was only possible because of their help and the enthusiasm and really that to make possible all of these experiments and the data analysis also, and also the funding, of course. And thank you very much for being here, and thank you for your attention. I will be happy to answer any questions you have.
Thank you, Ella. So questions, comments, curiosities? Yes. I think we have to use the...
Thanks very much, Ella, for the very nice talk. I had a question about the size of the objects that you see in the first technique you showed with X-ray diffraction. So, I mean, as I understand it, kind of once you've got the nucleation and then the crystals start to grow, then you'll start to observe the peaks in the diffraction. How big are those crystallites that you start to see?
You mean in the in-situ X-ray diffraction standard experiment? Well, I don't know how, probably the first layer, I don't know if you could see the first layer. The beam size, it's around 200 microns. So,
yeah, but I mean,
I don't know,
but the actual
yeah, the sensitivity of the signal. No, I think
I mean
the
X-ray diffraction, yeah. So, because you need a correlation length, right? So, I mean, in a way, it's saying how much is that, no?
Well, this is not, I mean, to correlate really GSACs directly with the in-situ XRD is not really possible because we use different concentration of the samples.
No, I don't mean that. I mean, you need a certain number of unit cells before you get a diffraction peak, right? So how?
We'll have to think about it. I don't know. Have any idea of?
I mean, with XRD here already, with few nanometers, you have already signals. So in synchrotron, we are assuming that the first layers we are seeing already 5-10 nanometers we should see. Now our samples are about 400 nanometers a standard, and that means that we can really see from the full growth. Of course, what we cannot probably see is what we are trying to do with the GSACs, which is the islands. But as soon as we have a layer, which probably is about 5-10 nanometers, we are already able to see it.
Thanks, Ella, for the nice talk. Before my curiosity, I just want to say that analyzing the shape of the peak, you can imagine, or you can try to get how many layers are you seeing. But okay, it's another question. The first curiosity is that when you have shown the video of the X-ray diffraction, there is a shift of the peak of the YBCO. So, how is that? Which is the origin of this shift? Can you say anything about that?
Well, the Repco phase, when it grows, it grows, of course, but then it also starts incorporating some oxygen, right? So it gets oxygenated in the way. So this makes the peak actually shift in the 2 theta because of the...
The second curiosity, maybe it's a little bit more difficult for you to answer. This is for the GSACs, it's in any small angle in general, it's quite important to know very well which is the noise that is coming from the. I mean, the noise is crucial to be able. Yeah, it's crucial to take out the noise correctly. So, have you done blank measurements?
Yes.
Okay.
So we have done even, we perform all the growth on only STO with no sample, for example. That would be one background we can do. And then also in the data analysis, there are some techniques to use that you can subtract the first frame from, for example, for us would be of every segment of the TILA growth, probably would have to subtract the first frame. Like before the heating starts, we subtract this frame from the following. And then after the jump, the first one maybe also could be subtracted to extract the changes between. But this is also not maybe totally correct. But now we have to think of how to do it correctly. But we have seen the STO blank experiments. But however, STO, we have seen also that depending on the on the orientation of the STO, because we have steps probably, this may affect the GSAC signal. So this is now very troubling for us, how to do it correctly. Because every samples will be oriented differently, and we cannot know, we would have to do AFM first or after to see what's the orientation of the steps or other features. So
maybe
it doesn't seem easy. That's why this ongoing analysis, and we will have to try to extract the signal and back it by AFM, so we are sure what we're seeing in GSACs is the real thing.
And last question, or last curiosity, do you think that ALBA 2 will help you?
ALBA 2 will help us for sure. First of all, if we keep going to NCD, we will have a new detector, and probably it will be a faster detector and more sensitive detector. The signal will be much higher, so also we will be able to measure higher signal to noise ratio. No? So we will be more sensitive. Many things will help us for ALBA 2.
Thanks.
I think CLAES also will get some upgrades, which I'm not sure about what they have, but
just to add some small thing related to the GSAC. So yeah, clearly this is very challenging, but it's true that for a process that is able to go from 50 nanometers per second to 5,000 nanometers per second, which means that the nucleation density has to change a lot from these 2 orders of magnitude. It's very interesting if we can really have access to this. Because, I mean, that means that depending on which conditions we will be, we can really have very high densities of islands or very small, or we can have also with the rare earth being the one which is dissolved in the liquid and determining the supersaturation. The rare earth will control also which is the size of the nuclei. And of course, this we cannot do by FIM in situ. So we can only see the final stage, right? And on the final stage, we have all the cooling process. So we have all the coarsening during the cooling and so on. So if we could have access to nucleation densities from the synchrotron in situ platform would be really a very interesting thing for TILAC and also for the community in general, because it's something which is really, breakthrough.
I think it will be difficult. It's challenging, but of course we can get there for sure with some strategies.
More questions? Yes.
Curiosity. Well, you measure the resistance, but why is so interesting to measure the resistance? Because I see in the evolution of the resistance some peaks that don't correlate with anything.
Well,
why do you give it?
No, the resistance curve, of course, correlates with all the phases we have. No, so if the metallic or the non-metallic changes to metallic phases, no, so all of this is in this resistance curve. And what is most important for us here is at the jump moment when we get this sharp. Maybe I can go back. Let me see. It will be easier to explain maybe here, or even, I don't see it, where is it? Oh, here. So you have this is the conductance, no? So inverse of the resistance curve. So this is around the jump moment. So you can see very sharp change at the jump moment, which is connected to the growth of the Rebko phase. And from this, we can calculate the growth rate. This is the most important for us here, to be able to calculate confidently the growth rate. It's better than from the intensity increase from the XRD. But yeah, also the different, you mean like here, no? This is because of the phases transformation that happen.
So this, for instance, this peak in resistance is because you are transformed?
Well, this particular was, I don't know if that was, ONA still is analyzing to be able to say with confidence. This one, this is the one troubling us, yes. But,
okay.
The other features, they can correlate kappa O to kappa 2O,
yes.
The change of the resistance. But it's true that this one, maybe it's
this one.
de-gazing because it's occurring at very low temperatures, and maybe
something. Okay, I was fixed with that.
Yeah, because the first decrease
happens here.
Yes.
Okay.
But I think
You only fixed on the one that is the one we
One
don't
thing
know.
which is the most important thing for the resistance is the one that allows us to really synchronize all the experiments from different beamlines and also from our setup here at ICMAB. Because it's where we have in every place we have the in-situ resistance, also here at ICMAB, and therefore we really can know where it's happening things because we have a one single measurement synchronization also.
Yeah, and if the shape, everything is the same. Yeah.
Another curiosity, so you explain with the XAS, you get different balance of copper, but do you use a specific model because you say 1.6, 1.5, so how do you calculate this?
Well,
do you use multiplet calculations or it's what is the model?
Well, we developed a method in calculated done based on the reference spectra of the full copper +2 and full copper +1 in our films.
Like
so it's a simple, yes, it's just the intensity comparison between two extreme values. It's quite simple.
The very interesting point here is that the liquid can get any oxidation state of the copper, while you cannot have it in solid. In solid, you will only have one or two, but in the liquid, you can have them all. And this is, in fact, what you can see here, that depending on the conditions, you can really move. But yes. More questions, comments? Yes?
Well, it's related to the measurement of resistance. How to measure resistance in a liquid? I don't know, maybe it's a silly question, but maybe you can lose the contacts, or what do you have to consider for that?
Well, we can measure because we do. That's true. And the liquid is very short-lived and it's very viscous. So this also helps. And of course, we were at the XAS beamline at 60 degrees or 40 degrees, and the liquid, even though it forms, it doesn't go away, let's say. It sticks to the substrate. So this is, and it doesn't affect really the contacts now, because they are prepared the way that ONA does, that was really optimized to the long time, let's say, optimization in order to be able to do that well.
Yeah, just a comment here. It's a good point, actually. So it's a shame there's an electrochemist in the audience, but I guess it could be ionic current.
The peak, you mean?
Yeah.
Oh.
You know, because it could be ionic diffusion, right?
But this is not in the liquid, it's before, it's the solid phase. It's the solid phase transformations. Yeah.
Yeah.
No, so in principle, let's say it has been a quite complex way to mount the contacts with gold and titanium gold contacts, which they don't have on top they don't have the YBCO. Okay, so we have pads which we can have access after the deposition of the layer. Okay, but also then let's say that we have all solid reaction up to when we go to the jump, okay, and that is then resistance that can be measured. At the jump, you could lose if it would be a full liquid without no solid inside the liquid, it could be 1 second that you lose, 2 seconds that you lose the resistance, but you don't see it. Yeah, you don't see it. But also the point is that all the yttria that we put in the material is not dissolved in the liquid. It's only dissolved a very small part. And as we keep growing the YBCO, the more yttria is dissolved in the liquid. So there are always a lot of, it's a semi-solid, if you like. It's a liquid with a lot of solids. And that probably also makes that this resistance, it's still possible to measure. But it's true that also with the binary systems, that is where then the question for me is very interesting, okay, when we do not have ternary. So there we generate a liquid. Did we have problems with the resistance on the binary sample? We don't have resistance in binary samples, exactly. So that may be something that we could do the same, but put in the resistance in binary samples and see what happens when we get into the liquid with the resistance.
Actually, we wanted to that, right? But
with a very short time, 1 second, 2 seconds, we don't see the difference. Yeah. More questions, comments? You want to add something, Ona?
This liquid, because I I have heard this several times, but it's always very fast, and I don't understand. This is a metastable liquid, or this when you show this liquid phase? This is a equilibrium diagram, or is a out of equilibrium diagram? No, but because I understand that you reach the liquid by one way of accessing this is you fix the temperature and then increase the partial pressure of oxygen suddenly.
That's what we do.
And then you have a liquid, and then at the same time, if I understood well, but I'm not sure, you start having the precipitation of phases, right? So for me, this tells me that this is a metastable, transient metastable.
Transient liquid, that's what we...
That's what you call transient.
Transient liquid.
So it's like a...
It should not be there.
Should not be there.
But it is.
The stable phase is the YBCO, so we should not form the liquid. And that's why nobody had tried to do this before. The point is that what we saw is that it was possible because it was faster to form the liquid than have the solid reaction between the precursor phases to the solid reaction to the YBCO. So the point is that as soon as you form the liquid, immediately you get into the stable phase, which is the YBCO. But the liquid, if you don't have the ternary, so if you don't have the rare earth, this is a stable liquid.
That's
so
why
barium and copper, in these conditions, they form a liquid. The point is that you have to be able to form this liquid before you do the solid-solid reaction, which is very long, and that's why you form the liquid, but immediately...
That there is small...
No, so what you see also in CHAS, that with the ternary you also see the kinks of the spectra of the liquid, is that you first form the liquid, then you immediately form the YBCO. That's we also see in XRD. You see that crystalline phases disappear, and then immediately you get the YBCO. It's impossible otherwise. A solid-solid reaction is never at 5,000 nanometers per second. That's why it had to be a liquid. Now, the good point is that with a binary in CHAS, we could see the liquid. If you do the same, you don't have here the spectra. With ternary, you see that you lose it. You see immediately that you get it back. So you see a liquid in a short of a second, and then or 2 seconds. Of course, if you go to the 20 nanometers per second, you can decrease the conditions to form slower, and then you have more time to see it. But in principle, it's something that also that microstructure you see that is Rickett-based because you have very flat surfaces. So there were many indications, but with CHAS experiments, I think we could demonstrate that.
But we also did the XRD experiments in situ with binary samples, and that's where we don't see any signal, but we see a little grains that reorient all the time like the little precipitates of the barium copper 202 or barium copper 02 phase. So we are quite confident it is actually the liquid.
More questions, comments, curiosities? No? Then we thank Elar again. And thank you for your presence.